welcome everybody. Last lecture today, summary, recap, closing the bracket, looking back what we learned, what we didn't learn, what the goals were of the lecture, how many of them were achieved. Footnote, not all of them. Let's start with this introductory slides I showed to you in mid-October when we started. It was the first slides that I presented. And those are the objectives I presented, and don't want to go through that. But if there's one slide I wanted to really achieve, that was this thing. And again, I watched the talk on this Monday in the systems space. It was all on the left side. Yeah, mixing the different abstraction layers. So there's something physical, there's something conceptual, there's something on that level, and that, and completely crazy, yeah, and completely missing the boat that, hey, this already exists, that already exists, and not just by merging the two. It's not a new thing. It's not true. It's two existing things being combined. Yeah? And so for me, it's really important to get these abstraction layers right, and for you to get these abstraction layers right. And there was the motivation also to get rid of C++ in the first place. And I think that worked, to my understanding. So none of you ever complained about the project. That's really a new record, because typically we had like 1 or 2 people per week complaining about our project in all previous iterations. I didn't hear a single thing. So maybe you all, I don't know, were so impressed. Oh, I don't dare to say anything, but no one, not a single email. That was fantastic. Yeah. For me, it was super cool because, I mean, I was coding in parallel to writing slides, and at this level of lecturing, as we're doing, the core lecture is the idea is to introduce you to the research stuff you're doing. You know? And sure, yeah, I mean, it's kind of the foundation for all the thesis work we do in my group. But what happened also in my group was, while coding, while for the first time ever trying to code the algorithms in Python, we bumped into so many interesting topics and things that could be improved and could be done differently. It was really crazy. Yeah? It was really, I want to do, I have to do the lecture, or I really would like to finish code. No, I can't do, because I have to do the lecture. I was always torn apart, like, how do I give a lecture the next day? It was really cool. Yeah? And to me, this coding on the project, you probably noticed, worked till Christmas, and then I gave up. Yeah, so mostly the slides you saw in January were like old slides, and I didn't have time to code anymore, even though I had so many ideas. For instance, the checkpointing thing. So while doing the logging slides, we completely revised the old recovery algorithm, with what we designed here, and we didn't code it. And then there was a bug in checkpointing. The slides I showed you on checkpointing have a bug. That doesn't work like that. And why is there a bug in that? Because I never implemented that, and I never wrote a unit test. Yeah, then that's how you introduce bugs. Yeah, so don't worry, checkpointing will not be part of the exam for this particular reason. I need to implement it, fix it. Right, that's how it is. Yeah, but that's the fun of systems work. Yeah, you can think about these things, yeah, get ideas, and the interesting thing in this field is really, it's not like you sit in your office and have ideas and think about that. You should start early on to try out things, to implement stuff. Only while trying to do something, you see, oh yeah, this doesn't work, I have to do it differently. Or you get another idea, oh, why not do it like this? Yeah, that's a cool idea, go for that. Yeah? It's not this strict separation of, like the stereotype about researchers and professors, like in a white lab suit and thinking, maybe scribbling on the blackboard, and then never implementing, or just implementing it very late. Like this waterfall model you maybe heard about in software engineering. The strict, it's complete bullshit, it doesn't work. Yeah? So it's really this highly iterative interaction, and the important thing is really start doing stuff, start trying things out, build prototypes, code, think about that. And as I also try to teach you in this course, software design is so important. Try to reverse engineer or re-engineer or refactor your code. It gives you so much insight. It's really insane. It's really incredible. It's not just for the beauty of it. It gives you algorithmic ideas, and it happens so many times in the project for me and my PhD students at least. So for me, it was an interesting endeavor. Right, yeah, and I think I would stick to that. kind of model. Yeah, so but can have a Q&A. Maybe you can also give me more feedback on that if you haven't done. Yeah, so we did a survey a couple of weeks ago for the people here in class. I will put a link online. If you haven't filled out the survey yet, please do it online in the next 2 days. It's really important for us to get feedback on what went wrong, what went well, and stuff like that. Good. Yeah, so those were the topics we planned. And we basically looked at all of these topics. So how should we do that? We don't have too much time today. My idea would be to briefly go through the slides. I don't know, just highlight some of the slides. What just happened? So that would be my idea, but of course it's too much content for 90 minutes, and maybe spend some time for questions. I could also alternatively scribble something on the blackboard, give you a different view on that. I don't know. What are your preferences? Recap on the slides, many slides, or different view and start with the blackboard? Blackboard? Who's for blackboard? Or who's for slides? Who says I don't care? Okay. Maybe slides and blackboard? Yeah. Just skimming through slides is boring. I don't know. Sorry. Let's do something on the blackboard and here and there show some slides. Yeah. So MBCC was previously part of the lecture taught in end of January or something. We started with MBCC because it's at the core of everything. It's really the heart. It's really in the center. The center of the universe, the center of the galaxy was MBCC. All about how to store things anyway, how to represent data in databases. The data is at the end of the day about storing stuff. Yeah? So how do we even do that? And we started with the key value store, got rid of the relational model. So I didn't focus on the standard database course. You will see a lot of tables, and there's tables, and then we extend it by columns to have version information. You don't need all of that. This can be done completely agnostic to the data model. And that is the advantage here, is that all of the stuff you learned in this class is completely independent from the data model. You can do it on all kinds of data. So basically, we built this MBCC store on top of the key value store. And the main insight was just, rather than keeping a single version that's updated in place, we just append a new version if we update. Yeah? We keep on appending versions very similar to Git. And that basically was the main storage format of our versioned key value store. But then, keeping in mind the ACID transactions, the ACID semantics, okay, we had to worry about how the heck would we do that. And that is done through MBCC. MBCC is a class of algorithms for concurrency control. And we had to, in particular, make sure to get the I right, the isolation between transactions. That's what we've spent a lot of time with, and then thinking about when it would be correct to commit a transaction and when not. So MBCC has these 3 phases. Where's that? Here. These 3 phases. A simulation phase, when the transaction was started with a begin transaction and is doing some stuff, it's sending an insert, maybe a select operation, update, and whatnot. At some point, the transaction says commit, and then it enters the validation phase. Yeah? So once you send a commit from a transaction, you enter validation, and then the database system has to find out, is it allowed? Is it okay if I commit the transaction, yes or no? And if it's okay, which means the transaction is validated successfully, the transaction is allowed to commit, and that means its changes will make its way into the committed version, into the main branch. If you go back to this Git versus MBCC talk Sue gave here in January, it's very, very similar what happens here. Your transaction is your feature branch. You open your feature branch, you do stuff on your feature branch. Eventually, you want to merge back to main, or rebase onto main. But that only works under certain conditions in the database system. You must not have You must not violate the isolation property, only then it is allowed. Yeah? But other than that, it's very similar to what Git would be doing. Yeah. Snapshot isolation is a major property of MVCC, similar to Git. Yeah? You see only what happens on your feature branch. You do not see concurrent things that are going on other branches. However, when you try to validate, you go back to the main version. Yeah? Then you have to take these effects into account. Yeah? But this fact that you are in your bubble, on your feature branch, in your transaction, that's called snapshot isolation. Your version of the data is a snapshot of the data as of the point in time when you started your transaction, when you forked your feature branch. And that's a term for that. Yeah, then we looked at these two different validation algorithms, schedules, and so forth. Yeah, we had exercises on that. Make sure to look at the exercises. That's important to understand these algorithms. Right. 2 was already, yeah? You could simulate something like that if you wanted. You get these things for free, that if you fork a transaction with your snapshot, you only see committed data as of the time when you started your transaction. Now, if you want to go in this zone in between, let's phrase it like that, where you see intermediate states from other transactions. Yeah, that's basically what the isolation levels reflect. Let's say read uncommitted. Then you could change that, in fact, but that would also mean that you violate the snapshot property in a way, because then all of a sudden you would be reading stuff that's different from what you read when you started your snapshot. Yeah. All of these discussions with isolation levels are kind of super dated. I don't see, it was done a long time ago as a compromise to have better performance. Yeah, but I would never ever do this again. And for a new implementation like ours, here in the Python database system, I mean, Sue is also implementing a prototype where she's integrating into isolation levels, but I would not do it. Really, with the hardware and the problems we have, it's very special cases where you need to fiddle with the isolation level tuning knob. If in doubt, don't do it. Just set it to serializable. You know. Okay. Yeah. Then we looked a little bit outside the bubble. So in particular, these how databases are used these days, on-premise, aka hosting. And the hosting is not the same as on-premise. Is really it's in your backyard. You put it in a room in your data center. Hosting means okay, you rent a physical server somewhere. And then you have these different levels, all depending on which of the services are outsourced to a company or which of the services are provided by yourself. It's a very common model these days called cloud services. Amazon Web Services was one of the first to start that a long time ago, but now there are many other services, in particular in Germany. There's Hetzner, for instance, and other companies kicking in also due to the political situation, providing alternatives for US companies. And we talked about the different trade-offs there. The database management system is just one layer in such an architecture. Yeah? And again, it's the same trade-offs for you to think about, okay, you host it yourself, you operate database management system, you provide a database administrator, you make sure that the updates get installed. If there's any problem, you make sure you care about that, or you put it somewhere at the responsibility of the service provider and say, okay, you care about that. Yeah? I have, for instance, database as a service, or runtime as a service, or application as a service, so you don't have to care about that anymore. Yeah, so it's like, we have this pizza example here that is along the same lines, but it's basically the choice whether you do stuff yourself or you call someone to fix it yourself. And there are trade-offs. I mean, I'm not sure if any of you ever tried to get, I don't know, an electrician or anyone else fixing someone in your house, it's not that easy. Yeah, you give a couple of phone calls, maybe someone appears and says something. Yeah, so one electrician says, you have to do it like that, and then you, what? And then you call another electrician and he says the complete opposite. Yeah, so you get different types of recommendations. It's not so easy. It's not just you order, you get the service and everything is fine. That's not how this works. It's also with problems. And the same with cloud providers. Of course, cloud providers claim, yeah, it's 100% up and it's super secure and everything. No, there were major outages for Amazon Web Services. It brought down major parts of our infrastructure. So things may happen. Yeah? It's not an easy choice, and you have to think about that carefully, how to do that. But the major advantage of these architectures is that in general, it might be the better choice, because before you buy and build a data center, a separate building, get physical servers, get administrators fixing the stuff, get the security right. Security is a killer these days, not performance, but getting the security up and running that no one steals your data. Every day we have new reports on data being stolen on the internet, and it's often simple configuration errors. It's in most of the cases, the choice will be you better get a cloud service provider on as high level as possible. That's the easy choice. But for certain situations, you want to do stuff yourself, but then you have to get the personnel and the right people to have it up and running. It's a design space. There's no single answer for that. Okay. Yeah, and then this other feature you get is elasticity. So there's this saying that in such an architecture, how do you scale it in the event of performance issues? Yeah? If you have your data center in your building and then you all of a sudden have so many more customers and your servers become slow and you want to scale it up, that will take a while. Maybe you have to buy a new data center, maybe you have to get new servers and so forth and so forth. And it takes a while, maybe some of the servers fail and whatnot. So in contrast, in the cloud environment, it's so much easier to scale up the system. And that's called elasticity. Yeah? Having an elastic backing of your application. You can relatively quickly get more virtual machines, and if you don't need them, you just discard them and stuff like that. It's really flexible to handle the load of your system. That's called elasticity, and that's one of the biggest advantages in such a cloud environment. Yeah. Right, yeah, and then we looked a little bit into the architecture of a database system itself. We started with a slide like that. So now coming back from our on-premise hosting or cloud architecture, there's something like an application sitting on top. Could also be the ORM, the Object Relational Mapper, and there's an API, SQL, and there's a database management system. That's one layer here, and underneath we have key value stores. In other implementations, it may be file systems, but for the context of this lecture, it's of course everything is key value stores. And yeah, and then you start building on that. Basically, inside the layer, you do stuff. Yeah? You have a key value store to represent your versions. You have your MVCC store, as I scribbled it on the board already. And then at some point, you have a query optimizer. So you have this facade pattern or wrapper pattern where the queries come in. And for the queries that are coming in, you don't send them directly to the store, but you might run the queries through an optimizer to come up with a better plan. And that's one of the big advantages of SQL, of course. SQL is fully declarative, and the database system has an optimizer which computes a program, which computes a physical execution plan, which, let's hope for the best, is efficient. Yeah? But that's the task of the query optimizer, which will, similar again to what a compiler for any programming language would do. Yeah? You have C++ coming in that's compiled into efficient code, and then the efficient code is executed. It's not the C++ text that's executed, of course. Yeah? Even for Python, that's precompiled to intermediate representations. Right. Yeah, and then we had a long session where I explained the interfaces of the database management system. So once you have this layer, yes, I can also show it here. We just had the slide here. Now we were there at the API level. I showed that in the Python code. Okay, now we have the interface. Obviously, we have interfaces where the SQL is coming in and the results that is coming back. Yeah? So that was our API here. And then I questioned that and showed you some examples why that interface has issues or is not ripe for certain tasks. Yeah? Talking about LLMs and AIs, you want to have an interface where you send natural text, be it in a textual representation or an audio or something like that, and the database system gives you the query result. Yeah? So there's actually research work doing exactly that, trying to replace SQL. You just say, I want to have all the lectures that professor gave in summer term 24, and then the LLM gives back the result by translating that, for instance, to a SQL query, sending it to a database system, and then the database system sends it back to you, and then the LLM presents it to you. Yeah? But then the question is, how do you do that? You could, of course, if the LLM sits on top, the LLM might be talking SQL directly, but you could also think about changing the interface to allow for natural text to be sent directly to the database system. And there are many, many extensions you can do along those lines. One is also this weird, super weird idea in SQL that whatever you return is a single relation. Yeah, so I presented that to you, how that would be. I mean, you take a number of relations, and whatever you do in SQL, you output a single relation. That's pretty weird design decision, which was taken at the time, and you understand it when you look back at how hardware looked back then. But you could change that, and that's what we showed in this slide. That actually this work was yesterday accepted at SIGMOD, which is the top international database conference. So let's see whether vendors pick up that idea, but I think it's an important change that should really be done in existing systems. Yeah, then was this one. Yeah, then the next step was to, okay, now we have these indexes. How do we add, now we have the store, how do we add indexes? Yeah? That's basically what we did in this slide set. So here we started with something like that, and now, okay, if we add indexes, no matter which indexes, be it simple diction, Python dictionaries, or B trees and whatnot, bitmaps, how would we add that? And that's how I showed it here. So you could have an indexing layer on top. You could write it like that if you want. We could debate whether we integrate it here actually, or put it to the side, it doesn't matter. But there's now some indexing probability. Yeah? So in our code, I already extended the MVCC store to also support indexes. And of course, that makes a lot of sense. Yeah? Because you don't want to scan the entire store for every query that comes in. It doesn't make sense. It's super inefficient, linear cost if your store's big. You don't want to do that. So you want to have indexes. And then we discussed about how to integrate that, what the effects of that would be, what the interfaces would be, and stuff like that. Yeah. Then we looked at the different types of indexes, and in particular B trees. This slide cannot be shown often enough. So this is really giving you a big overview on indexing. B trees can be used like for everything, can be adapted for everything. It's super versatile, more than 50 years old, but hey, it's so easy. This just works in all kinds of scenarios, on all kinds of hardware, all kinds of query problems. It's crazy. It's great. Yeah? It's the way to go for an external memory structure is typically B trees. Yeah, and so we looked at the different properties. I also showed you this top 4 index structures in database systems. The other is hash tables for any main memory situation. You could also use hash tables. We also used it when in the simple hash join. Simple hash join uses a hash table to build an index on the left input. But you can also use it as for any other type of equality index, of course. Again, keep in mind hash tables, standard hash tables can only do point queries. B trees can also do point queries, but in addition, they can do range queries. It's a major differentiator between these structures. It's very important to keep that in mind. Main memory database systems these days also use radix tries, trees and tries. Sometimes they're called tries, sometimes called trees, but it's the same idea. A compressed variant of that is called Artful. For instance, DuckDB uses Artful indexes. We looked at that a little bit in the Christmas lecture. There I introduced radix tries and had a spatial variant of that with the triangles. And we looked, and bitmaps, of course, is an important index structure for read-mostly scenarios where you really want to filter out tuples early on. And with bitmaps, you can combine them through logical operations. So we looked at different variants of bitmaps. Bitmap, there's a non-lossy bitmap, and then there's lossy bitmap. Lossy bitmap, aka Bloom filter, using hash functions to exclude parts of the data. Yeah, that's a big overview I showed to you with regards to indexing. Yeah, and then we looked at B trees. So I think from what I'm hearing from the exercises, you understand this very well. What can I say about B trees? So you have these internal nodes. You have a root node. You have internal nodes. We call it, here it's called inner nodes and leaf nodes. Inner nodes only have keys. Leaf nodes have keys and data, or pointer to data, key value. So if, key value store, each leaf here is a key value store, each node is a key value, each inner node is key value store, and so forth and so forth. Yeah, and then you can do point queries by whenever you search for a particular key, you start with the root, and I need to find the right subtree, and then you run down the tree just like in a binary search tree. Same ideas here, really the same. The major difference you have in a B tree is this linked list over the leaves. So that allows you to do an ISAM style access, index sequential access method. I think I have some note on that, some slide on that. I don't. It seems we had it somewhere. But basically, what that means is when you query for an interval for range, you just take the left boundary of the range, transform it into a point query, run down the tree, and from there you keep on scanning over the leaf level. You don't have to flood the entire tree with your recursion. You just do a point query for that range you're querying, and then you go to the right. While you're still within the condition, you return the results until once you run out of the condition, you stop returning the results. That's the entire trick here. I don't know, any questions about B trees? No, relatively easier topic. Yeah, then we looked at recursive model indexes. That's and I think I prepared that already in the B tree lecture a little bit. When you look at B trees, the inner nodes here are a model of the underlying data. We had a notebook on that where we did this counting, and I showed you, okay, the idea of such an inner structure of the tree. So if you take the B tree and remove the leaves, basically the B tree tries to make sure that the data buckets underneath have equal size. Yeah, it's trying to get what's called an equi-depth partitioning. Yeah, all partitions have the same or similar size. That's the idea of a B tree. So the inner nodes are a model of the data distribution. Yeah, and the more inner nodes you keep, the better the model will be. Yeah, the more inner nodes removed, yeah, if you take this root node as a model, that's also kind of a model, very coarse granular, yeah, not so precise, but the more inner nodes you keep on adding, the more precise the model is going to be. Yeah. And that's basically what leads to what's called recursive model indexes. The idea that, okay, we could also get rid of the inner nodes and just replace these inner nodes of the B tree as shown here by any other machine learning model. In particular, a regression model. That's what ARM-Eyes do. They allow you to get rid of all of these inner nodes and just replace it by a predictor function, by a simple linear regression, which makes a prediction where to find that particular key. So when you look up the key, you feed it into this function, and that gives you a prediction on where the key resides. And of course, you can do that in multi-levels. You can have one function here making a prediction, and then the next function here making a prediction, and so forth and so forth. At the end of the day, those predictions will not be precise. There will be an error, and you have to keep track, okay, what is the maximum error on your tree or on your subtree, and then you have to search within a specific range to get the correctness property. Yeah? So the interesting thing is, you might first think, okay, you can't use regression because it's imprecise, of course. Yeah? It will make errors. But if you build an error correction, you can, so regression plus the error correction makes it a correct method, a precise method again. And that's the interesting thing about ARM-Eyes. And you can gain performance with that, at least standalone. If you integrate them into a server, well, not so much. But it's an interesting point in the design space. And there's a lot of research happening actually in database systems trying to find out, okay, where can we use machine learning? So back then, when that was developed 7 or 8 years ago, it was all about deep learning, regression, classification, so the standard textbook machine learning models. These days, everybody is working on LLMs, of course. Yeah? It's, hey, what can we do with LLMs and stuff? Yeah? The interesting things you can do, for instance, there's one work that try to tune the database system by feeding database manuals into the LLM. They're trying to replace the database administrator. So you give, you have handbooks on how to tune your database system. You feed it into the LLM, and then make the LLM tune, set the tuning knobs of your database management system. Yeah? Why not? Yeah? It actually worked. Yeah. Right. So yeah, then we entered storage. Yeah, so it all starts with this storage hierarchy. So till that point, I completely ignored that, and we were in Python, and so yeah, it's very inefficient. Yeah? But if you, when you look at real database systems, you quickly run into the issue. Well, it's not the CPU, it's not my slow programming language. It's really the storage that's in the way. So the operations we're doing in databases are typically relatively cheap to do. Yeah, the CPU complexities are no killers. Yeah, simple hash join, linear complexity, sorting, n log n, merge join, once sorted is linear, lookups and hash tables, or one most of the time, lookups and trees, logarithmic costs, stuff like that. So it's not n to the power of 27 or something like that. Yeah? And the CPU is running like crazy. That's not going to happen. Huh? Of course, you can do, if you stack up a couple of nested loop joins, you can run a denial of service attack against the database system. That's fine, but that's typically not what you do. So what that means is, typically, if there's a performance issue in a database system, it has something to do with storage. It has something to do with the data cannot be shipped quick enough from some storage layer into the CPU. Yeah? So we are not CPU bound. The CPU is idling. The CPU is most of the time waiting for the data to be delivered into the CPU to do some meaningful processing. And the interesting thing is, this is also something, and people are doing that, that has to do with this von Neumann architecture, with this idea that there's a central computing unit and the memory is dumb. The memory can't do anything. Yeah? Whenever you do something, you ship it first. I mean, if you think about that, yeah, I mean, assume you organized a warehouse, whatever, an Amazon warehouse like that. There's one guy that can make decisions The warehouse is like, I don't know, 20 square kilometers. No one can decide anything. No one is allowed to think. Whenever some decision has to be taken, anything has to be brought to that one person to make a decision. Yeah? But whenever there's a parcel that cannot be, what do I do with the parcel? Ask the guy over there, just run 2 kilometers in that direction. There's a single guy who can do that. Yeah? Completely stupid. Yeah? Of course, then you can fix that by adding more people. Yeah? You have 10 women, 10 men distributed over the warehouse, and they can make decisions. That's the equivalent of adding more CPUs or more computing cores. Yeah, I understand. But if you increase that, you start questioning more and more, why the heck is compute and memory separated? Here is a computer that doesn't do that. Yeah, your brain doesn't do that. Storage and compute is highly intertwined. However, that works in detail, but it's not that you find a single CPU and a couple of SSDs and for Neumann-style architecture, and that's not there. It's intertwined. Yeah? And there are a couple of approaches in that space. Yeah? It's called processing in memory, PIM, approaches that do that. That tried to go a little bit in a different direction. But the classical architecture is something like that. I mean, there are newer developments now. At CIDR, for instance, at the conference I was at 2 weeks ago, there was a talk about recent hardware, and they're now stacking CPUs on top of each other like crazy, and they stack CPUs on the DRAM, and the distance gets closer. Yeah, so the price you have to pay for shipping memory to the CPU gets much smaller, so it doesn't hurt that much anymore. But it's still a separation. It's still CPU memory in most of the cases. Two different things. You ship stuff around. Yeah. So it's still this architecture. Just the constants go down. Yeah? Anyway, but that's something you have to keep in mind. I showed this analogy with this Twix bar and. Right. Yeah, we talked about good old hard disks. Yeah, it's still used for backup purposes or old servers. Sometimes you see that. It's a mechanical device. Just keep in mind, random access, super expensive. You move the disk arm over those platters. That's in the order of 2 to 10 milliseconds, depending on how far you move, depending on the price tag of the device. That's crazy. Yeah, what you do in whatever 5 milliseconds in your CPU. Yeah, that's a lot of time. A lot of compute you could do in 5 milliseconds. Versus sequential read and write is so much faster, and it gets better so much faster. Sequential read and write compared to this. Yeah, it's just physics. You just can't move that disk arm so quickly. Yeah. Okay. But for a real production system, you probably won't use that anymore. So you have some form of SSD, PCI attached, and whatnot. Yeah? So it's more like a leftover from an older, from other century. Yeah. We talked about splitting up the layers, non-uniform access rate. Of course, that is super important, and you see it all over the place. Yeah, once you make decisions on how to organize your storage, it's always some form of RAID. Yeah? Any server has typically some form of RAID underneath. The important thing are these different RAID levels. RAID 0, that stripes. RAID 1, that replicates the entire contents or blocks over the different devices. And then we had RAID 5, which uses this idea of computing a parity information. Yeah, for K disks, you have K-1 disks that have actual content and this extra parity block being stored. It's distributed round robin. The idea here is to avoid that you have, like in RAID 4, just one disk that has all the parity information, which increases the wear. Yeah? So which increases the likelihood that this disk fails. As whenever you touch any of those blocks, also the parity information has to be updated. You have more writes in this situation, and that's what you don't want to have. Therefore, you distribute it over all of the disks, and that is what RAID 5 is doing. Yeah? So here the parity is in some round-robin fashion. It's going from right to left. You can do it from left to right. This pattern is distributed over the different disks. That's the most common rate level you see. For larger systems, you can also use RAID 6, which has different types of parities. So RAID 5 can survive one disk failure. RAID 1 can survive all except one. Here it's only two, but if you had K disks, K minus 1 could break. As long as you have one disk, everything is fine. But of course, you waste a lot of time, waste a lot of storage in such a setup. So that's for typical backup on your desktop, that's something you might be using, but not for a server. RAID 5, you can lose one disk, same as in RAID 4. And then we talked about nested levels, and then I also added a separate lecture on that. I'm going to show how much of you saw that, where I talked a bit more because there was one question in this lecture, and then I went more into details on how to balance out the rate levels and what the effects are of the rate levels and stuff like that. So there's a lot of code about that in our repository. Right. Yeah, virtual memory talked about, page mapping, copy on write. That was set. Here I had a slide on PIM, processing in memory. Huh? Yeah.
What's the advantage of RAID 5 against RAID 4?
RAID 5, as I just said, in RAID 4, this is RAID 4. And now if you touch any of those blocks in the sense you write to any of those blocks, assume you write to block 1. Then you have to write to block 1 and this parity information, but not block 2. And same here, if you write to block 2, you don't have to write to block 1, but to parity. So no matter which block you touch here, you always have to update the parity as well, which means you have more write operations on this parity disk. And that increases the wear, and that increases the likelihood that the disk fails at some time. And that's what you want to avoid, and that's why you level it out to everybody has the same write load with something like that.
Do we have RAID 2 or RAID 3, or it's RAID 0, RAID 1, RAID 2?
Yeah, there are more levels, don't worry. So if you, maybe I recommend you check out the Wikipedia page. There are all kinds of levels also for historic reasons. There's RAID, I think one is bitwise striping or something like that, or bytewise striping. Here this is blockwise striping. That's for historic reasons. They don't play a role. They don't matter. It's really just RAID 0, 1, and 5. Sometimes you see RAID 6. Everything else is nesting the stuff in combinations somehow. That's the RAID levels you need to know about. So we learned about the storage hierarchy, and now if you have the storage hierarchy, and previously we learned about algorithms, so let's combine the two. And that's not that trivial. If you develop your algorithms to work well on a storage hierarchy, you enter a research space that's called external memory algorithms. Algorithms that do meaningful stuff, but behave well in the storage hierarchy. Typically, that's not how you start when you study computer science. You focus on CPU complexities and whatnot, and ignore that to a certain degree. But for database system, you can't do that because it might be that the data doesn't fit into main memory. And again, here's an opportunity to abstract things. So I introduced this idea to split it up into list queues and external queues. So from the beginning, develop your algorithms on an abstract queue interface, and then you can use them in main memory and in external memory. And that's what I showcased in our Python prototype. We looked at external merge sort as an example how to sort data that's bigger than your available main memory. The interesting thing about that is actually it's not external merge sort is not only useful to understand how to sort data bigger than main memory, but it also teaches you a lot about how to handle external memory anyway. There are all these fundamental operations you see, loading pages, merging pages, keeping priority queues to understand which page or which element to take next and send to the output, stuff like that. There's input buffers, there's output buffers. All of these ingredients you frequently encounter when developing these algorithms. If you understand this algorithm, you can develop many more external memory sort algorithms much more easily. Yeah. Oops, that was the last slide here. Then a separate slide. Okay. Yeah, and then I showed this example and how to external merge sort. There's these phases. There's this initial phase where you generate runs. So if each of these orange blocks is an empty page with 2 elements only, and that is your input file. What you do is you fill up your memory. Here it's 2 pages of main memory only. Fill it up with the data from your input file, sort it with the main memory sort algorithm, and then write that sorted data out to your output file. Yeah, now you have a sorted run, a 2-page run on disk/SSD. You do that for the entire input, so until you end up with, in this case, 4 2-page runs. And once you did that, you start merging this stuff recursively, level-wise typically. So here you can merge the 2-page runs. Here it's 2 you merge. You don't have to use only 2. You can also use more into 4-page runs, and so forth recursively. Yeah?
So this slide, so we have on the path 0, we have 2-page runs because we used 2 pages of
Yeah.
memory. But then there is a third page now.
Yeah, that's kind of a bit weird, I understand, yeah. So I said in the lecture multiple times, you need 3, basically you have different memory requirements. You have, for the run generation phase, the memory requirement is 1 page. For the merge phase, the memory requirement is 3 pages. And here I'm using 2 pages for run generation and 3 pages for merging. Yeah? To now make up a reason why that makes any sense, I would say, the operating system gave me more memory afterwards. Yeah? The real reason is, it's a bit confusing, I understand. Yeah? But if sure. Typically you have X pages, K pages, whatnot. I think we had a letter for that M pages of memory, and that's typically the same during run generation and during merging. Yeah? It's just important for you to keep in mind you need 3, at least 3 pages, because otherwise the merge doesn't work. And the number of pages you need in the merge is determined by the fan-in. We had that multiple times also. Yeah? That are your input streams, so your input runs, and then you pipe them into a merge operation. Yeah, then this is called the fan-in. And you need 1 page here for each input, 1 page. So fan-in, and then at least 1 page here, fan-in plus 1. Yeah, so if you have M pages, and you want to maximize the fan-in, it would be M minus 1 would be your fan-in, and so forth. Yeah.
For this graph, how many disk seeks would we have? Because I understand that there would be disk seek for each fan-in.
Yeah.
And for writing, so could you clarify that?
No, the filling up a buffer. Yeah, if you have a buffer like that, yeah. If that is your main memory buffer, consisting of, let's say, 3 pages. Yeah, maybe this is your input run, and you can keep the top 3 pages in main memory. You would, only once this buffer is empty, you fill it up. And then you would seek to that position, the next position there's a file somewhere, and of course read 3 pages at the same time. Yeah? So the smaller these buffers become, the more random accesses, the more random disk seeks you will have, both for reading and for writing. And that is why, from a theoretical point of view, to minimize the number of total I/O operations, you will always maximize the fan-in. You will always say, okay, the best configuration for this algorithm is to just keep 1 page for each input and 1 page for each output. But that will completely ruin your random I/O performance. In a real implementation, you will see, or even if you use a cost model that factors in random I/O, you will see the best configuration of external merge sort is rarely the one where you only have 1 page, 1 memory page per input and 1 per output. It should be more. yeah, then you pay the price that you might have more merge levels. Yeah, the fan-in goes down. Yeah, if you added 2 pages here, yeah, the fan-in would go down, but the I/O behavior gets better. Yeah. So it's not so easy to tune these algorithms. You can do it with a cost model, but I once did an experiment. You could really see that. Yeah, so it's really a problem with random I/O. Yeah. Okay, yeah, you merge. Eventually, you have this final merge. The important thing to keep in mind is you shouldn't blindly merge it into a sorted output file. It really depends on how you use this data. Taking a picture? Yeah, but not of me, please. How to use this data. Because the final merge could be done online. Yes, I think I had that. Come on, where was that? Where was that optimization? Somewhere, I don't know, I can't find it now. But this final merge here can be done online. Yeah? So you only have to merge on disk up to this point, and this final merge, the output stream of sorted elements could be delivered directly to the next operation. Yeah, in particular, if you have whatever sort merge join afterwards or sort-based grouping or something like that. So the final merge is online. You also see that in our implementation. And then the second improvement we talked about is this replacement selection, which is a beautiful algorithm which creates, in general, bigger output runs than you have memory available. Yeah, and I showed that in detail with this trick to have a heap and a list, and they share the same space, and the heap keeps on shrinking, the list growing, and so forth and so forth. It's a really nice algorithm, which increases the runs and therefore decreases the number of merge operations, or decreases the number of levels with high likelihood. Yeah. So, what was 10? Was 10 the Christmas lecture? Summary? Okay, so summary. Okay, the summary of part 1 or what? Yeah. Okay. Okay. Yeah, then we looked at bitmap indexes. I don't know how much I should repeat here. Run length encoding of bitmaps. I think I jump over that one. Yeah, I had all of these examples. Okay, how do you represent that? Core idea is always like, aha, you have a column, represent as a bitmap index. That means you have to collect all the different data values, attribute values that may occur. Here it's an easy case. You only have 3, only 6, 5, 3, 42, and 7. So you have these 3 bit sequences, also known as bit lists. So all of this is a bitmap. It consists of 3 bit sequences. That's how we call it in our code, or bit list. It's another option. Sometimes people say bit set. I don't like that because set has, to me, always this notion of not being ordered. But then the idea is that, if this data value is set to this value, you set the bit to true. Otherwise, you set it to false. That means in each of these rows, there can only be 1 bit set to true. All the other bits are set to false. And that's how you represent that. And with that, you can do all kinds of logical operations super efficiently, which can help a lot during query processing, of course. Yeah, and then the important variant of that we discussed is called Bloom filter. That's a compressed bitmap. Yeah? So here you have, like in a hash table, you don't have data in your hash array. You have bits. And for each insert, it's not really inserting the data, it's just marking it. It's marking the key in the Bloom filter. Say if you insert this key, then you run it, in this example, through 3 hash functions. The hash functions point to buckets. You set all of these buckets to true. And that gives you this probabilistic feature of a Bloom filter that is now you can use that for lookups. Yeah? The next time you look up this key, you run it through the same hash functions, you will find all of these bits are set to true, which gives you the information this key could be there. It's not saying it is there, it says it could be there due to collisions, because other insert operations could have set accidentally those bits, leading to a collision, leading you to believe that you inserted this element. But then you can tune these Bloom filters, and then you can decrease what's called the false positive rate of a Bloom filter, yeah, to bring down the likelihood that the Bloom filter says, yeah, it could be there, whereas in fact it's not there. Yeah? So these Bloom filters can be tuned by changing the size, the number of buckets, by changing the hash tables and so forth, also by using decent hash functions. Yeah? That's an art in itself, and so forth and so forth. So we looked at that. So and then word-aligned hybrid, so that's a different variant of compression we looked at, that you have these 63-bit chunks of net data, and then you have two types of representations of this is your original bit list you're trying to represent. I'm compressing per bit list, and the value is 12 here. So I always take a chunk of 63 bits, and if the chunk contains a mix of zeros and ones, I take that as a literal word, saying, okay, I just copy the bits to the output. That's my output literal, and I just mark it with this remaining bit. So I have 64 bits. The first bit is used to mark, that's a literal. 63 bits are following, take them as is. Or if you have many zeros, that are following in the input bit list, you mark, you send to the output a special word that's denoting the number of repetitions. Yeah? So here you say 1, that's meaning, aha, this is what follows is a number of repetitions. So there's actually a 0 pattern. So all of the following bits are set to 0. And this holds for that many 63-bit blocks. So this is binary 2. This means 63 times 2 bits are set to 0. Yeah? So like that you can easily compress all of these zeros, or if there were ones, you could also compress them easily. Here again is literal. Here again is 3 63 bits bit chunks. Yeah? Now you have a 3 here, of course, because it's 3 times 63 again marked with a 1, and here marked with a fill pattern 0, and so forth and so forth. That's called word-aligned hybrid compression. It exists in many variants. We showed one variant here. Yeah. What else can I show? Yeah.
Doesn't it make sense if we use a smaller chunks? I mean, as we have a lot of zeros, for example, we are not going to, when we want to escape some rows of zero, we are not going to escape 2 powered by 50.
Yeah. Yeah. So how do you start any answer in this class? It depends, right? Depends on what data you want to compress. So your argument is, I mean, here there's there's a single bit set to true, and everything else is 0. That ruins your day in the sense that you can't make it part of this repetition pattern. Yeah. So so here you have many zeros. It would be nice if I could compress these zeros. Also somehow. Yeah. So maybe depending on the distribution of ones, it would be better to automatically compute the optimal number of bits to use for that pattern in the first place. That's kind of what you're saying. Yeah? I'm hard coding these magic numbers. I'm saying, no, it's 63 bits. That's how I decided. I'm saying this marker here in the output denoting what is following, that's 1 bit. Why isn't that 2 bits or 3 bits? What if I have a pattern like 1 0 1 0 1 0 1 0 1 0? I mean, if I could represent something like that here with 2 bits, there's a 1 0 pattern following for 23 63-bit representations or 23 34-bit chunks. Maybe I could get a better compression ratio. Yeah? So this is totally hard-coded decision. 63. 64, of course, because it aligns super well to the architecture, and you can do efficient bit operations on that. But you're right, that you might get a better compression ratio by choosing these parameters differently. Yeah? Does it answer the question? Kind of, yeah? Okay. And there are papers doing this, yeah, playing with that and optimizing on that. Yeah, durability. Yeah, so that's the D that was missing from ACID. We looked at that. Yeah, I think I repeated that slide. So A and I, atomicity, isolation. Okay, we looked at that in the MVCC part. Consistency is orthogonal to all of this, but the D is kind of important. And that's, you have to be careful there. Yeah? That's why we looked at that. And then we basically introduced logging. Yeah? So as if we didn't have enough stores already, I added a third store, which is now the log, or I called it in the journal, in our Python prototype, I called it journal, to not confuse it with the standard Python logging, which you should use to keep track of what the heck is going on. Yeah? This journal or database log, that is the idea that you really keep track of each and every change operation, not the read operation. The change operations that happen in your database system are logged. And you first log, and then you modify the store on disk. That's very important, that this write-ahead logging. You write your log ahead of the database store. No matter what you do in your store or in your log, if it comes to persisting the stuff, to writing, you first have to write the log and then the store. Yeah, and that's a very important rule. And once you do that, the log becomes a single point of truth for the database system. Yeah, if you want to know what the state of your database system is, it's not the store, it's a log. The log is the truth in your database system. The store might be running afterwards. Yeah, and all decent database systems have this separation into log and persisting the store. Yeah, then we looked at this rule, important. Don't forget the second part. So in our implementation, we didn't integrate a database buffer. But once you keep integrating a database buffer, and we talked about the database buffer when talking about storage, a database buffer may evict pages. Yeah, so there's no room for a new page. You want to load a new page into the buffer. There's no room. You have to kick out an old page. So if the old page is dirty, it was written to, was changed by a transaction, at that point in time, you must make sure that the log records that reflect that change are written to the log first. Otherwise, you would violate this principle, the write-ahead log principle. Yeah? I think we had it, I can also write it here again, but yeah, you have the database buffer, you have your SSD, you have your buffer, yeah, you have a page. This page gets modified, and now you want to evict it. It's dirty, it was changed, you can't just delete it. You have to write its contents back to the store. And when you do that, you have to make sure you really flush the log records that reflect the changes that were done here. Otherwise, you may be in trouble. There are shortcuts around that and how we organize the store, but the general rule is this. Yeah? You have to keep that in mind, otherwise be careful what you're doing. Huh? So if in doubt, implement it like that. Yeah?
So this is an edge case because normally we just process a query, change something, and this goes through, but buffer decides for himself.
No, normally it doesn't go through. Think again the storage hierarchy. We had that when we have DRAM, whatever, DRAM and SSD. And the buffer sits kind of in between. Yeah. And then you do your changes on pages here, and you don't push it through while running the transaction. Yeah. So the general rule is you never force pages out. Even when committing, you don't have to force them out. Because if you force the changes out directly, you would lose the buffering property of DRAM over SSD. Yeah, you would pay the price for doing an SSD access. You don't want to do that. You want to be as fast as DRAM. So you try to avoid these writes. And that's a compromise, of course, because, okay, you're faster, but you might be losing data. Yeah? Think twice how you do that. Yeah? So, yeah, there's so many ways to organize that. Also with regards to durability of the transactions changes. Yeah. Okay. Yeah, maybe that's with regards to what we did in MVCC. Yeah? So we have really the simulation phase, the transactions send the operations to the store, and it's kind of intertwined, and one does that, the other does that. Yeah? Then you have validation. Yeah? One transaction validates at all times. Yeah? That's not two transactions validating simultaneously, it's only one. And that's equivalent to basically removing the actions of the transaction and replaying it against the committed version at that time. Recall that when the transactions run in their simulation phases, they're executed against their snapshots, some possibly old version of the data. But here, in the validation phase of a transaction, we check whether, okay, now you did this stuff in your bubble. Does that also work on the currently committed state of the database? On my current main, does that work? And if validation says, yeah, that's fine, the changes of the transaction will be applied to the database store. And that is similar to serializing these transactions. So that is what happens in the validation phase. So what happened here, this interaction of transactions, I don't care about anymore, because from the point of view of the log and the valid database state, this stuff in the middle is my valid database state. This is just optimizing, having multi-threaded execution while the stuff was running. Yeah, fine, nice, it's fast, okay. But from the point of view of correctness, this is what counts. And that is why this is what counts in the log. Yeah, so we, in our implementation, there's still this idea that for each change, for an update, insert, delete, and whatnot, there's a single log record. Yeah. So if you want to write a thesis about that. So all of these things were there's a couple of loose ends. I simply couldn't implement all of that during the semester. This is a loose end to look at. If you're interested in writing a thesis about that, bachelor, master, I think there's room for that. What else? Logging, stable storage. I just explained that on the board. Be careful to understand write-ahead logging. Yeah, fuzzy checkpoints. This idea that you keep track while running the system. Yeah, and this is inspired by this very old Aries recovery method that you still see in systems like Postgres or other disk-oriented database systems. So you keep track of what are my loser transactions. The transactions that didn't commit or did abort, and you keep track of the dirty objects, so objects that probably were changed in one way or the other, but were not persisted to disk. Those two structures you keep. And this is metadata about the stuff that's going on. And the main idea of fuzzy checkpointing is to persist that metadata to the log and thus speed up recovery. Yeah. So this leads to something that's called a fuzzy checkpoint. So when you look at standard recovery, you have this. Maybe we should first start with standard recovery. Where did I have that? Oh, that's here in this durability log, right? Durability slide set. Yeah, maybe start without checkpoint. Yeah. So here, as I explained it here. So with these three phases, we have the system crashed, maybe power failure or whatnot. You want to get back to a consistent state. What do? You do an analysis phase to find out, okay, what is the losers set? What are the transactions that didn't commit? And then there's this cleanup phase where you, here in a brute force fashion, for each object ID, you clean it up by removing work in progress entry, if that exists. If you persisted that, and we had that discussion a couple of times here, I probably wouldn't implement it like that, like in a standard database buffer. In a standard database buffer like here, you will always see this effect that a page may contain data from committed transactions and non-committed transactions. Yeah, so non-committed data may make it to disk in the store. This is one of the roots of all evil in these recovery algorithms because it makes it unnecessarily complex. Yeah, and it can be understood. given this was done in the 90s like that, and you didn't have so much main memory, yeah, and you wanted to optimize, I don't know, I wouldn't do it like that anymore. Yeah? So I would just persist something in the store that actually is guaranteed to commit, yeah, that passes the validation phase. And then you don't have this cleanup phase problem anymore, because work in progress entry cannot make its way into the store. Yeah, and we had the similar problem here with committed entries. Yeah? So when you validate a transaction, there's the simulation phase, validation phase, and the commit phase. Yeah, once the transaction validated, you make sure that all of its changes are appended to the commit entries of the specific object ID. And while if in that process something goes wrong, you could theoretically end up in a situation like that. Yeah? It would be better here to first push out actually the commit log record again and don't care about that. But then you would have to redo some of the commit entries again. Yes? So yeah, you have to be careful because it's not atomic. Yeah? How you do that in which order? You're moving around multiple entries for committed action, a transaction, but yes, things can go wrong and then you're not atomic anymore. And yeah, so you have to be careful with that in the implementation. And then you do the actual recovery, the redo. Here you make a forward pass through the log file. And you only look at winners here. Yeah? So you have to make sure that whatever winner transactions did found its way into the store. You want the store to reflect whatever the winners did. So this may mean that there's something in the log, an action marked in the log that didn't find its way into the store. That's what you're redoing. You're redoing something that was marked as, yeah, I did that. So you logged it, and then it's part of the truth. But then you look at the store and see, no, it's not there, even though it's in the log, which means you have to redo it in the store. That's the whole point of this thing. Yeah, right. Yeah, and then you have to also make sure to not reapply it multiple times. If it's a logical operation like increase the value by 1, you have to do it exactly once and not multiple times or never. Yeah? These kind of things. Yeah, and this is all inspired by Aries, of course, which is takes a different route. If you're interested, there are a couple of videos on my YouTube channel about that. Yeah, fuzzy checkpointing I will skip, as I said, because yeah, there's some bug. Want to implement it first and test it thoroughly. Good. Yeah, we talked about this Git versus MVCC. I mentioned it already. It was more like a research talk, but it has super striking similarities, and yeah, it opens up yeah, a space for thinking about what is the conflict in the database system anyway, or why don't we use nested transactions? We don't have that in database systems. Maybe we should. If we had, we could easily map a Git-style graph where a feature branch is forked from a feature branch into databases back and forth. But yeah. Okay. Yeah, then in the last 2 weeks, we looked a little bit at data layouts. So the most prominent data layouts being row and column layout. Column layout meaning you have large, you have tables with many columns, and rather than organizing, rather than organizing your data or linearizing your data in a row-wise fashion, you do it column-wise. So you have a storage structure at the end of the day that keeps all the data values for a single column or attribute, another storage structure for the next column, and so forth and so forth. And now if you have an analytical query that's not interested in all of the attribute values, but only in some, you're much faster, you have less I/O because you only read the stuff from this column. That's fantastic. This can also be compressed much better because it's the same data type, and maybe there are properties you can exploit in compression. Yeah, compression works so much better in a column-oriented layout. Yes, so this is where column stores are a good idea, and that's here. Well, where's my column? I know it's both row and column. Is this the row layout? Where's the column example? Here, okay. Yeah? So this is the kind of queries you see. Typically, you filter on a single condition, or you have just a few columns being selected. One is filtered on, the other is projected to, stuff like that. That's column layout. The row layout works a bit better if you have a transactional workload, or if you have many changes, insert, update, delete operations. Many modern database systems, however, still go for column layout. And you might pay a little price if you have updates, but keep in mind that many scenarios, the workloads are typically read mostly. There are not so many updates. It's more about reading this stuff. And if you want to optimize for reading, then probably column is the way to go. And the higher price you pay for updates in a column layout, then doesn't hurt so much. You can also optimize the layouts. There's work on that, longer story. But these are the two important layouts you will be seeing. And most of the stuff these days is column layout, actually. Right. And then we talked about compression a bit. Similar to compressing a bit list or bit sequence in a bitmap, you can also compress the base data. The easiest thing to apply is some form of dictionary compression. So in any situation where there's redundancy in the column, like here, you can do something like that. You basically split this table up into two tables. You can do that in SQL if you want. And then you just store these strings only once. And you can reconstruct the original table at any time by just joining these two relations, creating a view on that. So you pay the price for the join, depending on your query, but you don't replicate the data over and over again. And also, if you have any analytical query, you can do query processing on the compressed data. So if you look for all colleagues that live in Saarbrücken, the way to go is not to join this back to one relation and then filter on Saarbrücken. The way to go is you look up the city ID for Saarbrücken and then send a query on this relation, selecting the stuff where everything is equal to. That's much less I/O, in particular if this is represented in a column. Much less I/O, much easier to, much faster to process. So there are tons of mechanisms there that you can use. Run links encoding, well, not really. 7-bit, sometimes it works, but it's rarely used actually on this data or on the actual data and database. More important is 7-bit encoding. That's useful for situations where you have integers, for instance, with very different lengths, like something like that. So you have you could of course reassign the IDs. That's what I showed here. So keep in mind that an ID column in a relational database is typically artificial. And if that's only used inside the database system and not by the application, you could reassign those IDs. You could bring down your entire application doing that. If you miss just one place where someone addresses a particular ID in the table, then you're screwed. But in general, those IDs are artificial, and you should be able to reassign them at any point. And then if you do that, the problem is fixed, of course. But if you can't, you can do 7-bit encoding. Similar idea as in this word-aligned hybrid I just showed. So you have, from the 8 bits you have of a byte, you use 1 as a signal bit, which signals here 0, which means there's no other byte following. So these 7 bits represent the content, in this case, the integer, the binary representation of the integer. If this is set to 1, this means there's another byte with information following. And you have these sequences of bytes until the last byte eventually is marked to be 0. That's the ending byte. And then the content is always these 7-bit chunks concatenated that represents the number. And that's an efficient representation for integers of varying length. Right. Yeah, we looked at query processing algorithms, join algorithms, these classes of algorithms, yeah, nested loops, square complexity, index nested loops. So one of the inputs uses an index and the other is used as a lookup against the index. Sort merge, sort on the join attributes in both inputs, step through these two sorted streams in the merge join algorithm. And the other was partitioning, in particular co-partitioning. If you partition both inputs on the same condition, you end up, that's what a join is doing. So here, if that is your join condition, you try to match the tuples that have the same key from customers with the tuples that have the same key in City's dictionary. Those tuples build a co-group. Those two tuples and those two tuples are in co-group 1. Within the co-group, you do a cross product. That's your join result. And that's the core idea of these algorithms. And that leads to something that's called the generalized co-group join. A special case of that is Jim Gray's hash join, Gray's hash join. Yeah, tons of examples. Similar patterns can be applied to grouping and aggregation. It's all the same thing, basically. Sort or hash or partition, and then you're good to go. Yeah, then we had a very brief outlook on query optimization. So these two challenges, one is, how do I order my joins? I have binary joins. I should come up with an order. Here, denoted with two different plans, how to order those. The other is, okay, do I use the index or not? All of this is handled by the query optimizer, the cost-based optimizer that does all of this magic. We looked at design spaces, we looked at algorithms, we looked at these situations where you, at the end of the day, end up doing some sort of dynamic programming. So if this is your query on 4 relations, A, B, C, D, and whenever there's an edge, you have a join condition that's called the query graph or join graph. That is how you can represent your query. This is a filter on relation A, filter on relation B. This is a join being specified. If there's a thin edge, that means that's a cross product. Now, if you have a cost model, you can, using dynamic programming, try to come up with the optimal plan. And you do that bottom up here by first determining the optimal plan for accessing the tuples in A. You list all the possible options, and for each option, you feed that option into a cost model. The cost model will give you a number. And from these 3 numbers you get here, you keep the plan giving you the smallest number with the best plan. So like that, you can discard many plans and end up with something like that. And based on these building blocks, now you create bigger and bigger plans, now of size 2, using the stuff you did here for graphs of size 1. Again, list the different options, discard some of those, and so forth, until eventually you solve the entire query enumeration problem. That gives you a join order, and that gives you the best possible plan under your cost model. We looked at interesting orders, exploiting graph structure versus not exploiting. That's basically the point. Do I even want to consider cross products, or do I say I exclude cross products? There are many research works that optimize enumeration, ignoring cross products, but you should be careful. Actually, there are plans that use cross products and that are the optimal plans. So if you only look at those edges, ignoring cross products, you might trick yourself into believing that you found the optimal plan, whereas if you had factored in cross products, you would have found a faster plan. Longer story. So we also looked at pipelines, pull versus push, these kind of things, how to organize pipelines. On the slide running out of time. That was just less. This is something I shouldn't remember you. That was only happened a couple of days ago. You shouldn't have forgotten this stuff. So not sure. Short-term memories get slower and slower, get worse and worse due to these smartphones. Yeah, but it's important to keep in mind there are these pipeline breakers. You have this pull versus push organization. Pull is more if you have slow I/O. Typically, disk-based systems use pull-based pipelines. Modern systems use push-based, typically combined with some form of vectorization, meaning you don't push one tuple at a time, but you push a batch of tuples at a time. Also, what you see in the modern systems often is compilation. So you really compile your plan into an executable program. We had a Jupyter notebook on that I showed last time. Yeah, that was a tour de force through the material. Yeah, I hope you learned a lot. I hope you enjoyed it as much as I did it. Again, for me it was super stressful, but it was fun. So I have tons of ideas for follow-up work. If you're interested in thesis work, just approach me. Yeah, other than that, follow up. So there's no advanced lecture. We're giving next semester. Next semester, I will be teaching the undergrad lecture again. If you're interested in being a tutor, let me know. I also teach a pro-seminar called Gescheiterte Digitalisierung, Failed Digitization, in which I try to explain why Germany failed so hard in digitization. Yeah. I don't know, it's a pro seminar, I'm not sure whether you can bill it. So we have a seminar system. If it's listed for your program, you can attend. You should check LSF. So I think depends on your program. Yeah, other than that, I wish you good luck for Saturday. Friday there's no lecture. Have a good day. Thanks.